Welcome to another Talk Tensors Deep Dive. This week's paper on learning representations for tabular data distillation really grabbed my attention.
Oh, yeah.
Yeah, tabular data spreadsheets, databases, all that. It's kind of the unsung hero of machine learning. It might not be as flashy as image recognition, but this paper is tackling some really interesting challenges.
I agree. It's great to see more research in this area. Tabular data is everywhere, and figuring out how to distill those massive data sets without losing that valuable information, well, that's a big deal.
So for those who might not be familiar, what exactly is data distillation? Why is it important?
Imagine you have a giant library just overflowing with books.
Okay, I can picture that.
But you only have a small bookshelf to work with. Data distillation helps you choose the most essential books and create, summaries that capture the core knowledge. You get the essence without needing the entire library.
I love that analogy. Makes perfect sense. And for machine learning, this means what? Lower storage costs? Faster training times?
Absolutely. Plus, there's the potential for enhanced privacy since you're working with a concentrated version and not the raw data.
Now, the paper points out that distilling tabular data is not as straightforward as with images, which has been the main focus of distillation research. What makes it so tricky?
Images are pretty uniform, right? They're all about pixels, like a puzzle where every piece has the same shape. But tabular data, it's a mixed bag. You've got numbers, dates, categories, even missing values sometimes, all jumbled together.
So it's not just about shrinking the data set, it's about representing all those different data types in a compact way without losing their meaning and the relationships between them.
Exactly. And to make things even more complicated, tabular data works with a much wider range of models than images. Images usually stick with neural networks, but for tabular data, you might use decision trees, support vector machines, a whole bunch of different techniques.
Some of which might not be compatible with the methods used for distilling image data. Okay, so before we jump into the solutions proposed in the paper, let's talk a bit about the history. Dataset distillation is a relatively new field, isn't it? Where did it all begin?
Well, in its current form, yes, it's relatively new. But like many ideas in machine learning, you can trace it back to earlier concepts. One precursor is core set selection, where the goal was to pick a smaller set of data points that still accurately represents the original data.
So, like finding the most influential data points that capture the overall pattern of the data set.
Exactly. But core set selection simply picks existing data points. Data distillation takes it a step further. It aims to generate synthetic data that captures the essence of the original.
Okay, so not just selecting, but creating. Taking inspiration from the original data set and composing a new, more concise version.
Yeah, a great way to put it. And this really took off in the world of images with the rise of neural networks. Neural networks in computer vision, that led to a surge in research on distilling image datasets. Efficiency and scalability became big concerns.
But tabular data, as we mentioned, it has its own quirks and hasn't received as much attention.
Sadly, that's true. Despite its importance in tons of real-world applications, tabular data distillation is still catching up.
Well, hopefully this paper will help change that. Now, I've heard generative modeling mentioned in relation to data distillation. Are they the same thing?
That's a great question. They're definitely related, but with distinct goals. Generative modeling focuses on creating realistic data. Think AI generating photorealistic images or music that sounds just like a particular artist.
So it's about mimicking the original data as closely as possible. But data distillation, it's not about realism, right?
Right. Data distillation is about preserving informativeness. It's about creating a smaller data set that may not be identical to the original, but is equally effective at training those machine learning models.
Okay, that clears things up. So we've got this complex landscape of tabular data and a history of attempts to distill it. Now, I'm really curious to know, how does this paper tackle these challenges? What do they come up with?
Well, they introduced this framework called TDCallar. Stands for Tabular Data Distillation via Column Embeddings-Based Representation Learning. Yeah, it's a bit of a mouthful, but the idea is pretty cool.
TDCallar. Okay, I'm listening. What's so special about it?
The key here is using column embeddings. It's a technique they borrowed from natural language processing where words are represented as vectors. Those capture their meaning and relationships.
Embeddings. Right, remind me how those work.
It's like, think of it as translating words into this code that computers can understand.
Okay.
Each word gets a unique code, and words with similar meanings, their codes are close together in this numerical space.
Gotcha.
So king and queen would have codes closer than, say, king and apple.
So you're creating a map of words where the distance shows how similar they are,
Exactly. And what's neat about TDCallar is it applies this idea to the columns of data in a table.
So instead of words, you're creating embeddings for each value in a column.
Yeah.
Does that mean the model learns relationships between the values within a column? Like understanding that January and February are closer than January and Apple?
You got it. You're teaching the model the underlying structure and relationships in the data, really important for good distillation.
All right, following so far. Column embeddings, capturing the essence of each data point.
Yeah.
But how do they actually use these embeddings to distill the data?
Okay, so this is where it gets really interesting. Those embeddings are the building blocks for a compact, information-rich representation of the whole data row. They feed those embeddings into an encoder, it could be a transformer or a graph neural network, which squeezes the information into a smaller form.
Like juicing the data, getting rid of the pulp.
Haha. I like that. And you haven't lost those important flavors. Just like reconstructing a fruit from its juice, TDCallar uses a decoder to recreate the original data from this compressed version.
So they distill the data in this compressed form, making the whole process more efficient.
Yeah.
Makes sense. So I'm guessing they didn't just test TDCallar in isolation. They wanted to see how it compared to other distillation methods.
Right. They experimented with, clustering-based methods, model-centric approaches, even some core set selection methods.
A real mix of techniques.
Yeah.
Any standouts when paired with TDCallar?
The results were really something. TDCallar consistently improved the quality of the distilled data regardless of the method they used. Even with super small distillation sizes, like 10 to 100 instances per class, TDCallar made those tiny data sets incredibly informative.
Like TDCallar is a magic ingredient that makes any dish taste better no matter the recipe.
Yeah.
Love it. But were there any methods that seemed particularly well suited to this approach?
Clustering-based methods, particularly co-means, worked really well with TDCallar. Seems like the combination of compact representations and the way clustering groups similar data points was a winning combo.
So we've got those column embeddings going into an encoder, crunching the data down. And clustering methods perform well in that compressed space. But I'm assuming the choice of encoder also matters. They mentioned transformers and graph neural networks. Those are pretty hot right now.
Yeah, for sure. The encoder choice did affect performance. Transformers, not surprisingly, had the best results, but they're also computationally expensive. Graph neural networks were a good balance between performance and efficiency.
Classic trade-off. More power, more cost. Any other surprises in the results?
One that stood out to me was sometimes random sampling, just picking data points randomly, could be a surprisingly strong baseline.
Whoa, really? You're saying the simplest approach was sometimes almost as good as these complex distillation methods.
It does make you think, huh? Sometimes we overthink things when a simpler approach might work just as well. It all depends on the data and the task, of course. But it's a good reminder not to dismiss the basics.
I love those unexpected results that challenge our assumptions. Keeps things interesting. But beyond the technical details, I'm curious about real-world applications. Did the paper explore how this could be used in practice?
They did. They looked into a very relevant application. Hyperparameter optimization, HPO. It's a crucial step in machine learning where you're basically tweaking the settings of your model to get the best performance.
It's like finding the perfect settings on an espresso machine. So many variables to play with.
Exactly. It can be a very time-consuming and computationally expensive process. They found that using distilled data for HPO resulted in similar performance as using the full data set, but much faster.
Okay, that's huge. So not just theoretical improvements, but a real impact on how we train and use models in real-world scenarios.
Absolutely. It has the potential to speed up workflows, make the whole process more efficient and accessible.
Now that's exciting. So we've covered a lot: column embeddings, hyperparameter optimization. Before we jump into our novel notion segment and brainstorm some wacky ideas, let's recap. What are the key takeaways? All right, so tabular data distillation is a really promising area, some unique challenges, but huge potential. We've got TDCallar, this really smart framework using column embeddings to give those existing distillation methods a boost. Clustering methods, like amines, they really stand out. And of course, KDBench to help us evaluate future progress.
Couldn't have said it better myself. This paper really opens up some exciting new directions for research.
And speaking of exciting new directions, time for novel notions, where we throw out some maybe a little crazy research ideas inspired by this paper.
Okay.
I was thinking, what if we took inspiration from game theory, create a distillation technique where data points actually compete to be included in the distilled set based on how much they contribute to model performance across different tasks?
Oh, I like that. It reminds me of Shapley values, you know? They measure feature importance. We could maybe create a data point Shapley value to quantify its contribution across various tasks. The ones with the highest value would make it into that final set.
Yes. Survival of the fittest for data points. Only the most informative and versatile ones survive.
Cool.
Okay, here's another one. What if we use distilled tabular data as a form of data compression for efficient communication in federated learning?
Oh, that's interesting. Federated learning, right. Where models are trained on data that stays in different locations. No need to share the actual raw data. Big for privacy-sensitive applications.
Like training a model for medical diagnoses with data from different hospitals, but without actually moving any patient records between them.
Right, right. Sharing a compressed synthetic version instead of raw data could offer even more privacy protection.
It'd be like sending a secret message. Only someone with the key can decipher it.
Exactly.
I mean, these are just brainstorming ideas for now. But who knows? Maybe they'll inspire some groundbreaking research.
Definitely could.
And for our listeners, if you want to dive deeper, you can find a link to the full paper in the show notes. Thanks for joining us on this deep dive into tabular data distillation. We'll be back next time with another adventure in the world of machine learning.